China just invented a material nobody saw coming. Not a marginal improvement on something that already existed, not a laboratory curiosity that will spend the next 30 years looking for a commercial application, a genuinely new class of material that degrades completely in soil and seawater, performs mechanically on par with the petroleum-based plastics it is designed to replace, and can be manufactured at industrial scale using infrastructure that already exists across China's vast chemical production network. The implications for the planet's most persistent pollution crisis are enormous, and the implications for the industries that built the modern world on cheap, durable, disposable plastic are considerably more uncomfortable. The plastic problem. Nobody actually solved plastic is everywhere humans have ever been. That is not a metaphor or an environmental campaigner's rhetorical flourish. It is a precise and literal statement about the current condition of the planet. Microplastics have been found in the deepest ocean trenches on Earth, in Arctic ice cores, in the lung tissue of people who have never worked in a factory, in the bloodstream of newborn infants, and in rainfall collected in locations so remote that the nearest human settlement is hundreds of miles away. Plastic, the miracle material of the 20th century, has distributed itself across every ecosystem on Earth with a thoroughness that no other human invention has come close to matching. The numbers behind that distribution are staggering in a way that individual statistics struggle to convey. Since industrial plastic production began in earnest in the 1950s, humanity has manufactured approximately 9.2 billion metric tons of plastic. Of that total, roughly 9% has been recycled, 12% has been incinerated. The remaining 79% has accumulated in landfills and waterways, in ocean systems, and dispersed across the land surface of the planet in concentrations that scientists are only beginning to measure with accuracy. The global plastic recycling system, despite decades of public awareness campaigns, municipal infrastructure investment, and corporate sustainability commitments, handles a fraction of the material that enters it. Most plastic that goes into a recycling bin does not get recycled. It goes somewhere else and it stays there because plastic was engineered specifically to resist the biological and chemical processes that break down organic material. It was designed to last forever, and it has. The environmental movement has been pointing at this problem with escalating urgency since at least the 1970s, and the honest assessment of what has changed in response is not encouraging. Global plastic production has increased every single decade since the material was commercialized. The packaging industry, the agricultural sector, the medical supply chain, the construction industry, the electronics sector, essentially every major area of modern economic activity has become more dependent on plastic over time, not less, because the material's combination of low cost, lightweight, chemical resistance, and mechanical versatility has never been matched by anything that could be produced at comparable scale and price. The alternatives that have existed, glass, metal, paper, early bioplastics, have each failed to dislodge petroleum plastic from its dominant position because none of them could simultaneously match plastic on cost, weight, versatility, and manufacturability, until the material China's researchers have now placed into serious commercial development, the one that changes the equation on all four dimensions at once, what China actually built. China did not invent bioplastics. Let's establish that clearly up front, because the story of what China has actually developed is more interesting and more significant than a variation on materials that have been commercially available for decades. Bioplastics, plastics derived from biological sources like cornstarch, sugarcane, or cassava, have existed in various forms since the 1980s and have been commercially produced at meaningful scale since the early 2000s. The problem with conventional bioplastics is that most of them are bio-based, but not biodegradable, or biodegradable only under specific industrial composting conditions involving precise temperature and humidity ranges that do not exist in nature, in oceans, or in the municipal waste streams where most plastic actually ends up. a bioplastic cup that requires 60 days at 65 degrees Celsius in a certified industrial composting facility to degrade is not meaningfully different from an environmental outcome perspective from a conventional plastic cup that goes to landfill. What Chinese research institutions and materials companies have been developing, and in several cases have moved from laboratory demonstration into pilot production, is something structurally different. A class of fully biodegradable polymer materials that degrade under real-world ambient conditions in soil and seawater within time frames measured in months rather than centuries, without releasing microplastic fragments or toxic breakdown products in the process, while delivering mechanical properties, tensile strength, flexibility, barrier performance, thermal resistance that are genuinely competitive with the petroleum-based polymers they are designed to substitute. That combination has been the holy grail of materials science for 30 years. The research literature is filled with materials that achieve 2 or 3 of those requirements simultaneously. Achieving all of them in a single manufacturable material at commercial cost has been the specific problem that has resisted solution until now. The primary material class at the center of China's development push is polyhydroxyalkanoates, known in the industry as PHA. PHA is a naturally occurring polyester produced by bacteria as an energy storage mechanism under specific nutrient conditions. It is genuinely and completely biodegradable in soil, in seawater, and in the human body. It produces no toxic breakdown products. Its mechanical properties can be tuned across a wide range by adjusting the bacterial production conditions and the specific monomer composition of the polymer chain. And it has been known to science since the 1920s. The reason it has not replaced plastic already is not a mystery. The fermentation process required to produce PHA at industrial scale has historically been so expensive in terms of feedstock cost, fermentation infrastructure, downstream extraction and purification that PHA could not come close to competing economically with petroleum plastic produced at the scale the petrochemical industry operates. A material that costs 10 times as much as the thing it is replacing does not replace the thing it is replacing, regardless of its environmental credentials. China set out to break that economic equation, and the evidence from their pilot production programs suggests they are doing it. The cost breakthrough. Nobody expected cost is the whole game in material substitution. A material's environmental credentials, its performance characteristics, its degradation profile, all of those matter, but none of them override economics at the scale of global plastic production. The petrochemical industry produces plastic at a cost of roughly $1 to $2 per kilogram for commodity polymers like polyethylene and polypropylene, optimized over 70 years of process engineering and deployed across production facilities that represent trillions of dollars of accumulated capital investment. Competing with that cost structure from a standing start is the specific challenge that has defeated every serious attempt to commercialize sustainable polymer alternatives at meaningful scale. China's approach to the PHA cost problem has been characteristically comprehensive rather than incremental. Rather than attempting to optimize the conventional bacterial fermentation process for PHA production and hoping the improvements would be sufficient, Chinese research teams operating across institutions including Tsinghua University, the Chinese Academy of Sciences, and a growing number of well-funded startup companies pursued a parallel strategy that attacked the cost problem from multiple directions simultaneously. The feedstock question was addressed by developing bacterial strains capable of producing PHA from low-cost organic waste streams, agricultural residues, food processing waste, municipal organic waste, rather than from refined sugars and glucose that compete in price with food commodity markets. The fermentation efficiency question was addressed through synthetic biology approaches that dramatically increased the PHA yield per unit of fermentation volume. reducing the bioreactor infrastructure required per kilogram of output. The extraction question, historically one of the most energy-intensive steps in PHA production, was addressed through novel solvent-free extraction processes that reduce energy consumption and eliminate the chemical waste streams associated with conventional downstream processing. The cumulative effect of those parallel improvements demonstrated across pilot production programs at companies including Blufa in Shanghai and Danimer Scientific's Chinese joint venture operations has been a reduction in PHA production costs that industry analysts were not projecting to occur until the early 2030s at the earliest. Current estimates from Chinese producers with operating pilot lines place their production costs in the range of $3 to $5 per kilogram at pilot scale, with credible projections to reach below $2 per kilogram at full commercial scale. That figure, if it holds, puts PHA within striking distance of commodity plastic pricing for the first time in the material's history. Not identical, there remains a cost premium, but close enough that regulatory pressure, extended producer responsibility frameworks, and the growing corporate demand for genuine sustainability credentials create a viable commercial pathway. The gap that once made PHA economically impossible has narrowed to the point where it becomes economically negotiable. The companies leading the charge. Several Chinese companies are not just doing research. They are building factories, signing supply agreements, and shipping product into real commercial markets with a speed that reflects both the urgency of the government mandate behind this sector and the genuine maturity of the underlying technology. Blufa, founded in Shanghai in 2016 by a team of synthetic biologists from Tsinghua University, has built what it describes as the world's most advanced continuous PHA fermentation facility using proprietary bacterial strains engineered specifically for high-yield, low-cost production from non-food feedstocks. The company has commercial relationships with consumer packaging companies across Asia and is actively scaling toward production volumes that would make them relevant at the global level rather than the regional one. Kanghui New Materials, based in Jiangsu province, has focused specifically on PHA formulations for agricultural applications, mulch films, seed coatings, irrigation components, where the material's ability to biodegrade in soil without leaving microplastic residue addresses one of the most practically damaging and least publicly discussed plastic pollution problems in existence. Agricultural plastic currently covers an estimated 18 million hectares of farmland in China alone, and the conventional practice of collecting and disposing of that film at end-of-season leaves behind fragmented microplastic contamination that degrades soil structure and microbial communities over time in ways that compound with every growing season. A film that simply disappears into the soil it was protecting is not a marginal improvement on the alternative. It is a categorical solution to a problem that has no other credible answer at agricultural scale. Nature Time, a subsidiary of one of China's larger chemical conglomerates, has been developing PBAT, polybutylene adipate terephthalate, and PLA blended systems specifically formulated for high-performance packaging applications where the mechanical demands exceed what early biopolymer formulations could reliably meet. Their focus on the packaging sector, which accounts for roughly 40% of global plastic consumption by volume, reflects a strategic prioritization of the market segment where substitution would produce the largest immediate impact on plastic waste flows. And Terra Verde Bioworks, operating through a Sino-Canadian research collaboration, has been specifically working on PHA grades with the barrier properties required for food contact packaging, the application where conventional bioplastics have most consistently underperformed relative to petroleum alternatives, and where the technical bar is highest and the commercial reward for clearing it is largest. The government machine behind the materials. This did not happen organically. None of this would be at its current stage of development without the most sustained and coordinated government intervention in materials science that any country has attempted in the modern era, and understanding the structure of that intervention helps explain why China is where it is in this technology, while the rest of the world is largely still in the pilot project phase. The Chinese government formally identified biodegradable polymer development as a strategic priority in its 14th five-year plan, covering 2021 through 2025, allocating funding through the National Natural Science Foundation of China, the Ministry of Science and Technology's key research programs, and provincial-level science and technology commissions that operate with considerable autonomy and move money into promising programs faster than any centralized federal grant structure could manage. The regulatory lever has been just as important as the funding lever, and the sequencing between the two has been deliberate. China began implementing restrictions on single-use plastic items, bags, straws, cutlery, food service packaging, in 2021, creating an immediate and large domestic demand signal for alternative materials. That demand signal, guaranteed by regulation rather than dependent on voluntary consumer behavior change, gave Chinese PHA and biopolymer producers something that no amount of research funding can substitute for: a captive market at sufficient scale to justify the capital expenditure required to build commercial production infrastructure. The regulation created the demand. The funding created the supply capability. The combination created an industry that did not exist at meaningful scale 5 years ago and now occupies the most advanced position in the global biodegradable materials race by a margin that is widening with every passing production quarter. The science of actually disappearing. How a material disappears matters as much as whether it disappears. The distinction between genuine biodegradation and the various counterfeits that have been commercially marketed under sustainability adjacent language over the years is not semantic. It is the difference between a material that returns to the carbon cycle and a material that fragments into particles small enough to evade visual detection while remaining chemically persistent in biological systems. Oxo-degradable plastics, which were widely sold as an environmentally responsible alternative in the 2010s, turned out to fragment into microplastics under UV exposure without any meaningful reduction in the chemical persistence of the polymer chains involved. They made the problem smaller in particle size and larger in ecological distribution simultaneously. The regulatory backlash to that revelation shaped the standards framework that China's biodegradable materials development has had to meet, and the standards are considerably more stringent than what preceded them. PHA biodegradation in real-world environments is mediated by naturally occurring soil and marine bacteria that produce PHA depolymerase enzymes, the same biological machinery those microorganisms evolved to break down naturally occurring PHA produced by soil bacteria as part of the natural carbon cycle. This is not an engineered degradation pathway that depends on specific industrial conditions to activate. It is a biological process driven by organisms that exist in functionally every soil environment and in ocean surface waters globally. PHA items placed in marine environments have demonstrated complete degradation in timeframes ranging from several weeks to several months depending on temperature, microbial activity, and item thickness, compared to the 300 to 500 years typically cited for conventional polyethylene under comparable conditions. The breakdown products are water, carbon dioxide, and biomass. No microplastic intermediates, no persistent toxic compounds, no accumulation in the food chain. The material goes in and does not come back in a form that causes harm. What the petrochemical industry is not saying. The petroleum-based plastic industry is the largest and most profitable materials industry in human history. It produces more than 450 million metric tons of plastic annually, generates trillions of dollars in revenue across the value chain from crude oil extraction through polymer production, through packaging, manufacturing, and beyond, and is deeply integrated into the financial structures of some of the world's largest corporations and sovereign wealth funds. it is not going to announce its own obsolescence. What it is doing with the quiet efficiency of an industry that has managed existential threats before is buying time through several parallel strategies that deserve to be identified clearly. The recycling narrative has served the industry extraordinarily well for decades. The fundamental problem with plastic pollution presented through industry-funded public communications is not that plastic is produced in quantities that cannot be practically recovered and recycled. It is that people sort their recycling incorrectly. This framing has successfully redirected public concern toward individual behavior and away from production volumes for long enough that global plastic output has more than doubled since the first major wave of recycling awareness campaigns in the 1980s and 90s. The industry has invested meaningfully in advanced recycling technologies, chemical depolymerization processes that can theoretically return mixed plastic waste to usable monomers, and those technologies are genuinely promising at laboratory and small pilot scale. They are also, at current demonstrated economics, nowhere near capable of processing plastic waste at a fraction of the scale at which plastic is produced. The gap between the recycling capacity that exists and the production volume it would need to address is not a gap that incremental technology improvement closes on any relevant timeline. What threatens the petrochemical plastic industry is not better recycling. It is materials substitution at competitive cost. That is the scenario they have the least good answer to, and it is the scenario that China's PHA development program is building toward. The global race. China is winning. Other countries are not standing still. The European Union has invested substantially in biodegradable materials research through its Horizon funding programs, and European companies, including Novamont in Italy and Total Energies, Corbion, operating across Europe and the United States, have serious commercial PHA and PLA production programs. American companies, including Danimer Scientific in Georgia and New Light Technologies in California, have been developing PHA production technologies with genuine innovation content, and both have commercial production operating. The global biodegradable polymer market is genuinely competitive at the technology level, with serious research programs and commercial operations across multiple continents. Where China has established a lead that is structural rather than merely circumstantial is in the combination of production scale, feedstock integration, government demand creation, and manufacturing cost reduction that no other country's approach has yet managed to assemble simultaneously. European programs have strong technology but high labor and energy costs that make cost-competitive scaling difficult without regulatory mandates that the political environment has not consistently supported. American programs have strong innovation but fragmented government support and a petrochemical industry lobby that has successfully blunted the regulatory demand signals that would accelerate commercial scaling. China has all the pieces aligned at once: technology, scale ambition, government demand mandate, low-cost manufacturing infrastructure, and a domestic market large enough to absorb the production of multiple world-scale facilities. And it has them aligned in a coordinated rather than coincidental way. The trajectory this creates looks familiar. It is the same trajectory that made China the dominant global manufacturer of solar panels, of lithium-ion batteries, of electric vehicles, of consumer electronics. Build at domestic scale under government-supported demand conditions, drive costs down through scale and process innovation, reach cost parity or near parity with the incumbent technology, then expand globally into markets where the cost and performance case is now sufficient to drive adoption without requiring regulatory mandate. The biodegradable materials transition is earlier in that curve than solar or EVs, but it is clearly on the same curve. What happens to plastics world? Imagine the transition happening. Not all at once. Nothing in materials markets moves all at once, but progressively, sector by sector, application by application, driven by the combination of improving economics, tightening regulation, and the corporate sustainability commitments that are increasingly tied to real financial consequences through supply chain due diligence requirements and investor pressure. What does that transition actually displace, and what does it create? The first sectors to shift are the ones where the regulatory pressure is already highest and the performance requirements of the application are most compatible with current biopolymer capabilities. Single-use food service packaging, cups, containers, cutlery, straws, is already transitioning in markets where regulation has been implemented. Agricultural films represent a massive opportunity where the in-soil biodegradation property of PHA solves a problem that no other material class addresses effectively. Medical device packaging, where PHA's biocompatibility is an advantage rather than simply a neutral attribute, represents a high-value application where the cost premium is more easily absorbed, or cosmetics and personal care packaging, where brand owners face significant consumer pressure and are actively seeking credible alternatives, represents a market segment willing to pay for genuine sustainability credentials rather than the greenwashing that has dominated the space. The displacement for the petrochemical industry would begin at the edges of their portfolio, the applications where their cost advantage is already slimmest and the regulatory headwinds are already strongest, and then move progressively toward the core commodity packaging volumes as PHA and competing biopolymer production scales. That progression does not happen in 5 years. It happens over 20 to 30 years in a realistic scenario. But the petrochemical industry's strategic planning horizon is exactly that long. And the scenario they are watching develop in China's biodegradable materials sector is the one that keeps long-term strategists occupied with questions that do not have comfortable answers. China set out to replace plastic. That goal, stated plainly, sounds like the kind of aspirational declaration that gets made at international climate conferences and then fails to generate anything resembling commensurate action in the real world of industrial production and economic incentive. This time, the commensurate action is happening. The factories are being built. The feedstock supply chains are being assembled. The regulatory demand signals are already in place, generating real commercial volume. And the cost curve is moving in the direction that makes everything else possible. The environmental case for replacing plastic needs no elaboration. The evidence for the damage that persistent plastic pollution causes to marine ecosystems, to soil biology, to the food chain, and to human health accumulates faster than the policy response to it has ever moved. What has been missing is not motivation, not awareness, not international agreement that the problem is serious. What has been missing is a material that could actually do what plastic does at a price the market would actually pay. China's PHA development program is the most serious attempt yet to provide that material. Whether it fully succeeds, whether PHA at commercial scale and competitive cost becomes the material that genuinely displaces petroleum plastic across the applications where displacement matters most, is a question the next decade of production, scale-up market penetration, and regulatory evolution will answer. What is already decided is that China is further along that path than anyone else, moving faster than anyone else, with more resources aligned behind the effort than any comparable program anywhere. The plastic that built the modern world has a rival. It is being manufactured right now in Shanghai and Jiangsu and research parks across eastern China, and it does something that petroleum plastic, for all its extraordinary utility, has never once managed to do in the 70 years of its dominance. It disappears.